Hi everybody, Mr. Zarzak here, and in this screencast we're going to look at how we analyze two-dimensional collisions. Alright, so there's kind of two parts to this. There's the conceptual part of how we set these problems up, and then there's a bunch of algebra that we have to do. Okay, so I'll focus on what you need, is whether that be the concept or the algebra. Let's get started. Alright, so here's what we're going to do. We're going to look at a collision between two balls. We're going to model it as an elastic collision. All right, and then afterwards, we're going to look at what would happen as if it wasn't an elastic collision. All right, so here we go. All right, this is the idealized case. All right, we like elastic collisions because those conserve kinetic energy. When it comes to two-dimensional collisions, if we can apply conservation of energy, it's going to allow us to do a heck of a lot less math. And so that's what we're happy to do if we're allowed to do, but we can only do that if we have the express criteria that it's a perfectly elastic collision, or it's stated expressly in the problem that energy is conserved. Okay, which is what we're going to look at here. Okay, so for the elastic collision, that just means Ke is conserved. Okay, and so we're just going to solve this by applying conservation of kinetic energy. Okay, so I'm going to call this one mass 1. This is V1, so the 2 kilogram ball is moving at 5 meters per second. It strikes ball 2, we'll call that M2, which is initially at rest. All right, if we have information for after, so afterwards, ball 1 goes off at 3 meters per second, so that's that V1 prime to indicate after, okay, at an angle of 10 degrees above the horizontal, okay? Energy doesn't have any direction to it. All right, so we'll worry about that theta a little bit later on. So I'm just going to write my conservation of energy statement. So Ke1 plus Ke2. So two balls with two kinetic energies to consider. All right, afterwards, Ke1 prime plus Ke2 prime. Okay, so kinetic energy before is equal to kinetic energy after. All right, good news is ball 2 is initially at rest, so no moving, no energy of moving. All right, and so we have 1/2 m1v1 squared is equal to 1/2 m1v1 prime squared plus 1/2 m2v2 prime squared. All right, notice that each term has a 1/2. Okay, so because of that, we can factor out those 1/2. That's kind of nice. All right, and if we look at what's here, we know the masses, we know the velocity of ball 1 before, and we know the velocity of ball 1 after. So really the only unknown that's in here is this v2 prime. Okay, so not too bad. We're going to isolate that. Okay, so m1 v1 squared, and I'm going to subtract over this m1 v1 prime. Okay, and then I'm left on the right-hand side, m2 v2 prime squared. All right, so divide out the m2 into both sides and take the square root, and that should give me an expression for v2 prime. So m1 v1 squared minus m1 v1 prime squared divided by m2 square rooted. Okay. All right, so let's just go ahead and solve this. So v2 prime is going to be equal to the square root of m1, which is 2 kilograms, times its initial velocity squared, so 5 meters per second squared, minus 2 times, let's see, afterwards, ball 1 is going along at 3 meters per second. Okay, and then ball 2 just has a mass of 1 kilogram. Okay, so let's see, so 5 squared 25 times 2 is 50, minus, let's see, 3 squared is 9 times 2 is 18, 50 minus 18, so square root of 32, which if I put that in calculator, it's going to give me 5.567 meters per second. Now this right here, okay, this is just the speed. Okay, it doesn't tell me anything about the direction. Energy is a scalar. Okay, so now if all I'm asked for is for the speed, well then great, I'm done with the problem. If I'm asked for the angle, okay, you know, or if like, oh, what's the total velocity? So we need the speed and direction. Okay, well we can do this, but energy is not gonna work. So what we're gonna do instead is we're gonna apply conservation of momentum. So I'm back up at my original picture. I'm just gonna make a quick sketch of the components. Okay, and what I'm looking at here right now is, I mean, they're just arrows, but okay, we're gonna apply conservation of momentum. So these, oops, I don't want to do that. Go back to your home. Okay, these are momentum arrows. Okay, so ball 1 goes up and to the right, ball 2 goes down and to the right. All right, the conservation of momentum says the before has got to be equal to the after. All right, so I'm actually going to look at this from the perspective of the vertical momentum, the momentum in the y direction. All right, you'll see why here in just a second. Okay, so remember, momentum is a vector, so when I write out my conservation of momentum statement, m1, v1, y, I got to account for direction. So I'm only looking at up and down right now. So m1, v1, y after, or prime, m2, v2, y prime. Okay, the reason I'm going to do this is in the y direction is going to be easier because, well, ball one is only moving to the right to begin with. Okay, so neither ball has any momentum up or down to begin with. And what that really means, the consequence of this here I'm going to move over that m1, v1, y prime, is that the momentum of ball number one after in the y direction is equal to an opposite of, see, so I have to subtract it over, the momentum in the y direction for ball number two. Okay, and that's kind of nice. All right. So if I have this, if I go back to my diagram, okay, so now I'm going to put these angles in here. So like this would be like angle 1, and this would be angle 2. Okay, well, these pieces here, okay, so those are opposite of the angles. All right, and we're given one of the hypotenuse. So like for V1 prime, it's 3 meters per second, and for V2, that's that 5.567 meters per second that we solve for. So we've got the hypotenuse, these pieces, these y pieces opposite, so it means sine functions. Okay, so if I take this and I expand this out a little bit, so m1 times v1, I dropped a prime over here, sorry, v1 prime times sine of angle 1 is equal to m2 times v2 prime sine of angle 2. Okay, and in this, the only part that's unknown is this angle, which means I can solve it. Okay, and again, I'm going to get an algebraic solution here first. Okay, so I get m1 v1 prime sine theta 1, okay, divided by m2 v2 prime is equal to sine of theta 2. All right, and so theta 2 is going to be equal to the inverse sine of negative m1 v1 prime sine theta 1 divided by m2 v2 prime. Okay, so I told you at the beginning there's a bunch of math. All right, so let's plug in some numbers here. All right, so m1 is the 2 kilogram ball. Afterwards, it's going at, what was it? Was it 3 meters per second? Yeah, 3 meters per second. So 3 meters per second. All right, at an angle of 10 degrees above the horizontal, divided by m2, which is just 1, okay, times its speed after, which is this number that we calculated, 5.567. 5.567. Okay, so the inverse sine of that, which is a bit of a mess, but we can calculate it, and if we do, we get negative 17.877 degrees. Okay, and the fact that the angle is negative, okay, well, all that's happening is this is just indicating this would be like below the positive x-axis. Okay, so ball 1 goes up and to the right at 10 degrees. Ball 2 goes down and to the right and 17 degrees. All right. Okay, so again, we've got the idealized case where if it's perfectly elastic. Well, what if it's not? Okay, what if we took our two balls and we gave them like a rubber coating or something so that they had some grip to them? If they grip each other, that means they're going to kind of grab onto one another, even if it's just temporarily as they collide, which is going to make the collision non-elastic or inelastic, which means we're going to lose some energy. Okay, so we're going to go through this process again, except, well, in this case, kinetic energy is not conserved. And if that's the case, the way that we solve it is we apply conservation of momentum, okay, in 2 dimensions, which really just means more math. All right, so let's go ahead and do that. Okay, so I'm going to start with sideways. So m1 v1 x plus m2 v2 x is equal to m1 v1 x prime plus m2 v2 x prime. All right. Like with energy, okay, ball 2 is not moving to begin with, so no velocity, no momentum. All right, and then the other little kind of caveat to this, all right, is that ball number 1 is only moving sideways. Okay, so like that V1 is all X. All right. Afterwards, we have information about ball number 1. It goes off at 4.23 meters per second at an angle of 14.3 degrees. So when the two balls, when they collide somewhat inelastically, that means they stick a little bit. That's going to wind up changing the speed and the direction of the ball. So we're not going to get the same answers as we did before, which is why we're applying conservation of momentum instead of conservation of energy. Okay, so since I have this this V1 prime and I have the angle, okay, I'm just going to take my statement. So M1 V1x is equal to M1, and I'm going to replace that V1x prime. Let's see, so that'd be this piece, that's adjacent. So we got the cosine function. So this would be V1 prime times cosine of angle 1. All right, but I'm actually going to leave the V2x prime, okay, as it is, because ultimately I'm going to need to, now I've got one unknown. If I tried to plug in my theta for this V2x prime, well, then I'd wind up with an equation with 2 unknowns, which doesn't really help. Okay, it's going to be easier just to solve for this V2x prime. All right, so let's go ahead and do that. So I got M1 V1x minus M1 V1 prime cosine theta 1 divided by M2 is equal to this V2x prime. All right, so certainly something we can solve, so we're going to do just that, so V2x prime. Okay, so M1, that's the 2 kilogram ball. It's initially going along at, what was it, 5 meters per second. Okay, minus 2 times afterwards, its speed was 4.23 meters per second times cosine of 14.3 degrees. Okay, that divided by ball 2's mass, which is just 1. Okay, so if I shove that in the calculator, I'm going to get 1.802 meters per second. Okay, so I'm going to highlight that just so that I can go back and find it later. Okay, because I'm going to need it in a bit here. Because now that we've looked at momentum in the x direction, we're going to look at momentum in the y direction so that we can get the vertical component of ball 2 after. So M1 V1y plus M2 V2y is equal to M1 V1y prime plus M2 V2y prime. Okay, no up and down momentum to begin with. Okay, ball 1 is only moving sideways. Okay, and so kind of like we were looking at with conservation of energy, okay, the vertical part of ball 1's momentum after is equal to and opposite the vertical momentum of ball 2 after. Right. Now again, just going back and looking at what I have here. Okay, since I have the speed and the direction of ball 1, so I know the theta. All right, so that means I can solve for whatever component I want. So I can get the vertical piece that would be opposite, so it's the sine function. All right, that's what I need to get the vertical piece of momentum number 2. So that's exactly what I'm going to do. Okay, same basic trick I did, okay, in the x direction. So M1 V1y prime divided by M2 is equal to V2y prime, where I can write that M1 V1y as V1 prime times sine of angle 1 divided by M2 is equal to V2y prime. Okay, so I can get that piece. So V2y prime is going to be equal to negative M1, which is the 2 kilograms. All right, afterwards, we're given that its speed is 4.23 meters per second. It goes off at an angle of, was it 14.3 degrees? Yeah, 14.3 degrees. Okay, divided by 1. Okay, so again, it's just calculator time. All right, when I do this, I'm going to get a negative 2.090. Okay, which I would expect because ball 2 goes down and to the right, so I would expect a negative number with this. All right, and once I have these pieces of velocity, okay, well, if I know what my V2x prime is and my V2y prime, okay, well, then I can get all the pieces that I need now. It's just for my own purpose, I'm going to write this as here. So V2x prime, okay, it goes sideways. V2y y prime goes downwards. All right, so this v2 prime goes like that. Okay, so we're going to solve for the v2 prime, both the speed and for the direction. Okay, so to get the speed part, v2 prime, I'm going to use Pythagorean theorem. So I'm going to take the x velocity after and square it, add it to the y velocity squared after it, I'm going to take the square root. Okay, so I'm really just transposing my numbers from above. All right, so let's see. So the x number, what was the x number? 1.8022 plus that y value. Okay, notice when I squared, all right, the negative part, negative times negative positive, don't worry about that. Put it in your calculator, right, and you should get 2.759 meters per second. Okay, so there's the overall, there's the speed. Okay, and then for the direction, use inverse trig function, okay, just to get it. Now, technically, we're going to find the energy loss, so we wouldn't actually have to solve for the direction, but we've come this far, so we might as well look at it just for comparison. So v2y prime over v2 x prime. We've done so much math. Let's just do a little bit more. Okay, so then that would be inverse tan. Okay, so the y part, that was the negative 2.090. The x part, 1.8022. Put that in calculator. Okay, and we should get negative 49.225. Okay, so if we compare this to what we had with elastic, okay, we got different speeds, we got different directions. Okay, so we start changing the properties of the collision, we change the results of the collision too. All right, now, another way that we can see this, okay, oops, where'd that go? Go back. Is we look at the energy loss. So, sorry, I don't know where they just went. Okay, we're going to find the energy loss in the collision. Okay, so my diagram just got kind of messy there, so sorry. But that's okay. Need a little bit more workspace here. Okay, so anyway, so if we consider the energy loss now. Okay, this is why we can't apply conservation of kinetic energy, because we lose some kinetic energy. All right, so KE1 plus KE2 is equal to KE1 final plus KE2 final. If we plug in our numbers, it's not going to work out because there's some energy loss along the way. All right. Ball 2 is initially at rest. Okay, so at least that part simplifies down. Okay, if I start expanding this out, 1/2 m1 v1 squared is equal to 1/2 m1 v1 prime squared plus 1/2 m2 v2 prime squared plus that energy loss term. Okay, notice here I cannot factor out a 1/2 because there's no 1/2 with that h. Okay, so I'm stuck with it. All right, so ball 1's mass was 2 kilograms. Actually, here, you know what? Let's get an algebraic expression. I take it back. Okay, so then let's subtract over 1/2 m1 v1 prime squared minus 1/2 m2 v2 prime squared, and that is the energy lost in the collision. All right, so lots of subbing, but nothing that we can't handle. Okay, so here we go. 1/2. Okay, ball 2 has a mass of 2. It's initially going at 5 meters per second. Afterwards, the 2 kilogram ball moves along at 4.23 meters per second. All right, the 1 kilogram ball, all right, we calculated a value of, what was it, 2.579 meters per second. Okay, so if we plug all that into our calculator, we should get a value of 3.300. Okay, this is loss of energy, so that would have units of joules. All right, so we lost this many joules in the collision when it is partially inelastic. All right, that was a bunch. Okay, the concepts and then the algebra. Lots of algebra. Okay, not a lot of concepts, but the concepts are more powerful than the math. All right, or at least you can't have the math without the concepts anyway. All right, so this is Mr. Zarzik saying thanks for watching, and we'll see you next time.